Hi, I'm Owen Prysock, and this is my report on Lab 3 circuits. An introduction. So in this lab, we're using charge conservation principles, which we've learned in class, and these include Ohm's law, the loop rule, the node rule, and we're using these to predict the current voltage and resistance in both DC and RC circuits. So essentially, we're trying to get these values using these theoretical computational models as seen above, like Ohm's law, KVL, and KCL. And then we're comparing these with the actual values that we're getting in the lab. And so the results that we see are that Ohm's rule applies to DC circuits and that the charging and discharging of capacitors is not linear. So the first question is we're tasked to find the current at location I1 and location I2. So we know by the conservation of charge that these two currents are going to be the same, and we use Ohm's law to find out theoretically that it would be 0.02 amps, and we also found the same result in the lab, 0.02 amps. And if we flip the connections of one of the ammeters, it would just flip the sign, not the magnitude of the current, since the direction through the ammeter is opposite. So if we replace one of the ammeters with a voltmeter, basically stating that the voltmeter would be in parallel to the circuit, the voltmeter will measure the potential difference, which would be about 3 volts. And since the voltmeter has such high resistance, it's not going to pull any current away from the system, such that the current of the system is going to remain the same, 0.02 amps. So what is the voltage drop across each component in the circuit? So we found the voltage drop due to both resistors, and we can do this using Ohm's law. And we compare this to what we get in the lab. So there is very little difference between what we got theoretically and what we got physically. But there's also resistance in the ammeters, the battery, and the wires. So we had to use the loop rule, set all the voltage drops equal to 0, and that's where we found the voltage drop due to the extra resistance supplied by the wires, the battery, and the ammeter. So using these voltage drops that we got before, we use Ohm's law to find the resistance of each component. Just a little conversational piece here. If we had this ammeter that was in parallel to this 100 ohm resistor, we would find that the current going through the ammeter is higher than the 0.02 found when the circuit was just in a series. And the reason for this is because when a resistor is in parallel, there is another path that the electrons can travel, in this case, a less resistive path. So more electrons are going to travel through this path, this less resistive path, giving it more current. And here we see our graph showing the voltage drops and increases throughout the circuit. We see that it increases through the battery in series, and it decreases through both resistors and the ammeter. Now we move on to the second part of this lab, the RC circuit. So an RC circuit is where you have a resistor and a capacitor in a series in a circuit, kind of like this diagram down to the bottom right. And we see that it charges at a certain rate that is not linear, and it discharges at a certain rate that is not linear. So if we have a capacitor that is fully charged and we have a 2 ohm resistor or light bulb in this case, we're trying to figure out how long it would take to completely discharge. And in this case, we use the charging and discharging formulas, and we get that it about completely discharges around 8 seconds, which is consistent with what we got in our lab. Now, we have a 4.5 ohm resistor. So there's more resistance in this RC circuit, and so we see that the charging and discharging is takes a lot slower. So it takes about 16 seconds to fully charge, and it takes about 16 seconds to fully discharge, which is consistent with what we got in our lab. Lastly, what if we charge a capacitor with no resistance in the circuit at all? And how would our ideal model predict the capacitor to reach a full charge? And would this prediction actually happen in real life? So, if we had zero resistance in the circuit, we would see this exponential term over here would go to infinity. And so it would take 0 seconds to fully charge and discharge. Now, obviously, you can't have this happen in real life because there is resistance in the wires, even a little resistance in the battery, resistance, and even the ammeter that you're using to measure this. So we predict that it would take about half a second to 1 second to fully charge up in practice. Thank you for watching.